It's a pleasure for me to start the afternoon session, session number 7. We have 6 talks during the session, and the first one will be Jana Szpilkowa. The title of this presentation is the Global Pension Index in the Context of Multi-Criteria Decision Making. And please, Jana, start here. The floor is yours.
You some information about the Global Pension Index. And the Global Pension Index of a company Mercer CFA Institute based in Melbourne. And this company evaluates approximately 47 countries during the world. And this company studies a lot of indicators. And this Global Pension Index is composed from 3 sub-indices. They are adequacy, sustainability, and integrity. And we are going to concentrate on sustainability sub-index. Please observe. At this picture, you can see evaluation with respect to Mercer CFA Institute, Global Pension Index, and pension systems around the world. For example, the highest degree is highlighted by blue color. And you can see that with respect to this Mercer evaluation, the best pension systems have Iceland, Netherlands, and maybe here you can see something small piece. This is the map of Israel. And B plus has index on the level of this B plus grade, for example, Finland and Australia. And what is for us very important, please observe that maybe I can show you here Poland has grade C, and Poland was evaluated, is included in this evaluation approximately 3 years ago. So, and you can see also that grade C is for Italy and for Poland and for Brazil, for Grassalis information. And you can see, and very important for us is also our cooperation with our friends from Pamplona. And you can see that here we have a C plus, and also for France and USA, and maybe here you can see for Kazakhstan. And all white areas represents countries which are not included in this evaluation. And you can see here, maybe I use this one. This is Czech Republic, is white, and on the right side here is Slovakia, and we are not included in this evaluation. So that is the reason why we started to evaluate our pension system. Our friends from Prague try to want to cooperate with us. So this is the reason why I started to evaluate pension system in Slovakia. We know our positive part of our pension system, and we have a lot of negative part of our system. So the second reason why we decided to evaluate this pension system is that we want to include in these 47 countries. But I started to cooperate with head of Mercer Institute, with Mr. David Knox. And he sent me a lot of very interesting and important informations, but about weights of individual indicators, I have not any information. Please observe, you can see grade of the Global Pension Index. This is the newest information for 2023. And Netherlands maximum points 85 from 100 points. And then B plus, B, I have here a little bit a small mistake because Finland has grade B plus. And these colors doesn't represent the previous ones. I wanted only highlighted that Slovakia has this pension index, global pension index, on the level of 64.96 points. But this number evaluate me with my colleagues. And Spain, this number is from original publication of Mercer Institution. And here on the level of C is Italy. Poland has these points, Brazil here. And maybe for Dennis, information is here that Turkey and India has evaluation on the level of grade D. So it's very interesting, and we know how problems we have in this area. And I would like to remind some basic information about Global Pension Index. Once more, this Global Pension Index contains from three sub-indices, adequacy, and adequacy has 11 indicators, sustainability 9, and integrity 8 indicators. But it seems that it's very easy. But if you can see, sustainability sub-index contains 9 indicators. And the first one, coverage of the private pension system, represents proportion of working age population which save money in the private pension system, the second and third pillars. The second indicator is level of asset as a percentage of GDP. The third one, life expectancy at state pension age. You know, life expectancy, it's very important number because whole system evaluate life expectancy because you know that life expectancy grow and grow. And for one, funded mandatory contribution, for example, in Slovakia was up to now for 2023 determined value 6.5% from contributions to the social insurance company. But our political situation in Slovakia, I can say, absolutely changed. And our politicians decided that this funded mandatory contribution will be only 4%. It's very bad for savers. The 5, labor force participation for ages 55 to 64. 6, adjustment government debt and public cost of pensions. Access of older employees to pension savings. That means that people which work at retirement age, whether they can receive some part of their saved money from second and third pillar pensions. And of course, real economic growth, and very popular for me. It's I don't like this indicator because I think that something only institutions tell about environmental, social, and governance issues and involvement in their work, but I am not sure. So these 9 indicators we need to evaluate, and these indicators have stated some weights in original publication of Mercer CFA Institute. And I asked Mr. Knox by which way they determine these weights. So I didn't answer on this my question. For other question, I received reply, but for these weights, no. So that was a reason that we try to apply some well-known methods on determination of weight. I only remind you very quickly, maybe we can take uniform weights, but at this moment, uniform weights are apparently not appropriate for our investigation. And also some differentiated weights, we can apply subjective method, and in our presentation, you will see SATI method, exact SATI method, and approximate SATI method, and then method of pair comparison. Then there exist also some objective methods, and we can also apply some harmonizing methods, and we can aggregate some previous ones. This is very important numbers and values for determining of weights with respect to SATI methods. If our indicators, we can create some square matrix. In the row and also in column, we put our indicators. We have some square matrix, and then we assume if indicators in row and column are equally important, we can put number 1. If the row indicator is slightly more significant than the column one, we can put number 3. And then if the row indicator is much more significant than the column one, we can put number 5. And if row indicator is demonstratively more significant, we can put 7. And if the row indicator is totally more significant, we can put number 9. And these numbers can be extended about even numbers. But you know, a human brain is capable of distinguishing this very, very gentle is equally, equally, slightly more, much more, demonstratively more significant, totally. It's a little bit problem for our brain. So we must be very careful. Maybe we need some group of experts to know, distinguish these very, very gentle differences. So we try to determine this number without any special experts. We determine only about on the level of our knowledge. So we studied a lot of all this, all our previous indicators. Please observe, we have this matrix, this square matrix. So we put here number 1, number 3, 5, 7, and so on. And on the below the main diagonal are inverted numbers. So I am going to back a little bit later, and I am going to remind you so-called consistency index, because our matrix must be so-called consistent. So we need to calculate consistency index, which is given by this formula, and M represents number of indicators. We have 9 indicators, and this lambda max is eigenvalue of our matrix, but positive real eigenvalue. It's not problem to calculate because we need we have, without any problem, some online free calculators, and I have chosen one of them, and it's very easy because it's enough copy from Excel to this online calculator, and without any problem, I obtain eigenvalues. So our positive real eigenvalue is a little bit higher, 10.073, and corresponding consistency index is on this level. This is a little bit higher number. And there exists also so-called consistency ratio. And this consistency ratio we divided by this fraction. And there is so-called mean random consistency index. It's a very interesting number because experts on this area, on a lot of numbers by some special way, I don't know this way precisely, determine if we have 9 indicators, it is enough to put, instead of this mean random consistency index, 1.45. So if I divided this number 0.13 and so on, divided by 1.45, this number is 0.0925. It's a little bit smaller than 0.1. It's on the edge, you see. So we plan to maybe discuss more about original square matrix, about our values 1, 3, 5, and so on, because I feel that this number is relatively high, and apparently for our investigation will be if we will study and we will decide between these numbers and evaluation to the of all indicators, and we will try to state some new matrix. So, but this number satisfy our conditions. And if we want to determine weights, we apply in MS Office Excel function solver, and we put this function. And you see from this formula, nonlinear optimization problem, and we assume that our weights must be strictly positive numbers and normalized that sum is equal to 1. So without any problem, if we apply this function, we obtain this weight, which is highlighted here with green color. You can see control, we have normalized weights. So it's a well-known procedure, and then very often, you know, you have experience that some functions which are now in the Excel and maybe in Words and in some other programs, you know that some of these functions are deleted and maybe they are substituted by others. If we have not a solver, you can apply so-called approximate SATI method. So we have the same matrix, and then we calculate geometric mean for each row, and there is you can see sum of this column, and weights we state without any problem each value divided by this sum. There is control that we have normalized weights. Then we tried to calculate using method of pair comparison. So we compared only 2 indicators, and if we prefer indicator from the row, we put number 1. If we prepare or we give higher significance two indicators from the column, we put 0. And if we assume that if both indicators have the same level, we put 0.5. So here you can see that these numbers represent sum with respect to rows. And this is very special cell. You can see that we have 0. So we assume that our result will be positive weights, not non-zero. It's enough put add, for example, number 1 to each cell, and then we can determine normalized weights if we divided each number from this column divided by 45. So control, we have number 1. But we calculate these weights with accuracy on 7 decimal places. And we was surprised. You can see here, exact Satis method for our indicators. We have weights here with approximate Sati method here, and method of paired comparison. We have weights in the third column. Yes, we determine 2 minutes. Okay, so I finish. I only compare with Mercer CFA Institute for comparison, because I wanted to determine whether weights which were determined by Mercer company will be the same, maybe with very, very small differences. And here, if I put on 2 decimal places, normality was violated. So we assume some compromises. If this yellow cells, we put 100 plus to this value to be this weights normalized. This is only last information. If we put weights which was determined by Mercer Institute, sub-index sustainability for Slovakia is on the level 54.5 points from 100. With exact Sati method, 52.9, approximate method, 52.6, and method of paired comparison, 52.3. So we have also numbers for Spain, but we know to come back to our original matrix and discuss this evaluation 1, 3, 5, 9, 7, and 9. And similarly, like Martin Stepnička yesterday, I would like to ask you, and if you want some other methods, and maybe using fuzzy numbers. I know that there exist some methods using fuzzy numbers, and maybe so-called basic uncertain information and others. We will be very glad if you help us. Thank you so much.
Thank you very much. Any questions, remarks? I only want to be sure that this, if you have created this matrix with these numbers, these numbers were put by you and your team, yes? Yes. So we're talking about this one. These numbers were put by you, yes?
Yes.
Okay. But with discussion with some your group or just alone?
No, I have colleague and also Mikkel. So this is about my feeling. Okay. I decided that for me is, for example, life expectancy the same important like some other indicators, but only from my personal experience. Okay. But I have not.
But maybe this would be nice also to discuss with our persons without showing them your matrix to see what would be the answers or other persons here. Maybe just to compare how it works. Okay. Okay. Thank you very much. Any questions? Any other questions? If not, once again, thank you very much, Jana. Thank you. Okay. And I have forgotten to say at the beginning some announcement from the Lazio. Please register for bus trip as soon as possible, but not later than tomorrow at 9 morning. And now we can go to the next, to the second speaker. This second speaker will be Dimura Grasalis from Brazil. And that's the joint paper also with the Spanish group. We have many authors here. But by the way, the first one, yeah, the title of the presentation is Optimizing Self-Attention Through Aggregation Techniques. And
this is the overview of the presentation. So I will briefly explain the awareness and in particular the self-attention. And then explain how our optimize the self-attention and the awareness. Things are kind of taking then some particular sets, some preliminary results. So transformers, okay? Transformers have been proved very efficient in various texts and applications. For example, natural language processing and computer vision. Computer vision is the particular interest of my students, okay? So, in particular, the architecture of the transformers enables parallel training. So, some tasks can be done in parallel. So this can accelerate the learning process compared to sequential models. In particular, the attention mechanism enables the efficient modeling of long-range dependence in sequential data. So overcoming limitations and drawbacks of recurrent architectures. So then one of the key features driving the performance of the transformers is, in fact, the self-attention mechanism. The transformers presents two parts, the encoder and the decoder layers. And these are the five main elements of those parts of the transformers. The input embedding, conversion of the inputs from words or tokens into dense vectors of real numbers. Positional encoding, it's when the information about the position of the words in a sequence is incorporated to the inputs. Then the multi-head attention allows the model to attend to different parts of the input at the same time. So using for that multiple attention heads. Then addition and normalization involves adding the output of a sublayer of the original input, followed by a normalization step, and finally, feed forward performs linear transformation operations, followed by an activation function operating in an independent way at its position in a sequence. So Let's take a look just at the encoder, okay? So the first part here is the embedding inputting, when the words or tokens are transformed into dense real vectors. Then the position, some information about the position of the words in a sequence. And then here is our segmentation mechanism, okay? Then add, normalize, feed forward, add, normalize, okay. It doesn't matter if someone is not comfortable with this transformer, because I'm not too, okay? I just know this sufficient to help with some theoretical ideas, okay? So let's see the self-attention mechanism. This mechanism allows the models to assign different weights to different parts of the input, highlight the importance of various elements in the sequence, in the data sequence. The most common approach in transformers is to use multi-head attention. So this allows the model to learn different attention at the same time, attention representation at the same time. This enhances the model ability to capture complex patterns and relationships in sequential data. Now let's take a break in transformers and let's briefly recall some concepts. Fuzz measure, that is a set function in the intervals 0, 1, okay? That is increasing, bounded, and normalized. Using the fuzz measure, you can define, for example, this aggregation function, that is the discrete Choquet integral, okay? And you have a lot of presentations of Choquet integral, but here, just observe that here you have a sum of products, okay? Sum of products. Then, going back to the self-attention mechanism, this is the self-attention mechanism can be defined like this, okay? So the inputs are 3 matrices: the carry matrix, the key matrix, and the value matrix. All of them are obtained by multiplying a kind of weight matrix by the input representation, but this weight matrix here are not important, okay? I'm not going to explain them or to talk about them. So here, we proceed a softmax of this expression. And here, these values, just to normalize and to put these values into 0, 1 with some characteristics that I'm going to talk now, and then multiply by V. Okay, so let's simplify. So our proposal is to optimize this self-attention mechanism, okay, based on the Choquet integral. Let's see. So to simplify the notation, denote this part here, this matrix is by M, okay? So the self-attention mechanism is just a product of matrices, but not any matrix. Well, V can be any matrix, but M is a matrix with some important properties. For example, here, M is a right stochastic matrix. That is, it's a real square matrix with each row summing to 1, okay? The sum of the elements of each row of M is equal to 1, okay? So observe that it's that the product of a matrix is defined in terms of a sum of products, okay? So having this in mind, so you can define the following fuzz measure. Since the sum of the elements of each line of M, the matrix M, is equal to 1, then you can take, think in a line and in how the product is done, no? A line and a column. So you can take each element of the line, and each element of the line you can define as the measure of the unitary set composed by the corresponding element of the column, okay? So the matrix M is a matrix of the measures of unitary sets of the matrix V. Then, when you, for the first measure of any non-empty subset of the column, of the corresponding column, okay, you just sum the corresponding unitary measures, measures of the unitaries, okay? So if you have the column, complete column, then sum 1. And of course, if you define that the first measure of the empty set is 0. So this is a simple first measure construct from the elements of the matrix B. Then take such column as the input of a Choquet integral. You can define a matrix, okay, which each entry is a Choquet integral of the corresponding line and column. So you have a matrix of particular Choquet integrals. Okay, it's easy to understand. Then, look, the self-attention mechanism that a product of matrix, then it is transformed as a matrix of Choquet integrals. Each entry is the Choquet integral of the corresponding column, considering the line of the matrix M. Okay? So let's now know the data sets we used to validate this transform with this new proposed self-attention mechanism. The first one is the data set called CFAR10. It's the data set is a large data set composed by 60,000 color images with a resolution of 32 by 32 pixels and divided into 4 different classes, okay? It's considered a challenge for the traditional classifiers because the images are too small and usually with low resolution, okay? Now let's complicate and consider the CFAR 100. Well, CFAR 100 presents the same amount of images, 60,000, but it presents 100 distinct classes. So it's a more complex data set because for each class you have a few amount of images. So it's more difficult to train to traditional classifiers, okay? And it presents more complexity for the training text. And then this data set, Caltech 101, is more and more complex than the others. It's more complex than the other because notes that it has just 9,146 images for 101 classes, okay? The images are very small and there are several real-world objects in the images, okay, and different. So it's really complex to work with these data sets. Now, preliminary results. So using the first data sets, we use 2 kinds of metrics here. the accuracy, the higher the accuracy, the better the model, okay? And on the right is the other metric, is the loss. That is just the opposite. The lower the loss, the best the method, better the method. Wow. Here are the results in training on the left, and on the right in validation. I know that the figures are too small, but doesn't matter. You can see that there is no difference between our method and the vanilla transform. Okay, both methods performed, but there are no difference here, and the same behavior when using this data set. Okay, it's not possible to say that the methods are different considering those two metrics. But when you consider the Caltech 101, that is the more complex data set, you can see here a difference in training, okay? I asked Joelson this figure is too small for me. And then here you can observe better. It seems to be a short difference, but for this kind of models, this is expressive. Okay. Then these are of course preliminary works. You have to try other data sets. Okay. And then from now, you can conclude that this new attention mechanism seems to perform better in more complex data sets. That is when the vanilla transformer becomes to be more with less accuracy. For example, our model can show best performance. Okay. And for simpler data sets, as the two first ones, simpler. They are complex, but simpler in this case, okay? The performance remains similar to vanilla transformers. I know that you are going to ask me about the performance in time, no? But observe that the vanilla transformers, if you see the architecture in the implementation in a low level, the implementation is prepared for matrix operations, okay? Operations on matrices. Then all the optimization of the implementation is done for that. So what Joelson did, he implemented everything from the beginning, okay? And now the model is implemented, optimize the implementation for the Choquet integral. That is reusing some parts of the code. I don't know anything about implementation, but something like that, okay? He has everything documented if one wants to replicate, for example, the experiment, but he went in a low level and obtaining these results. And the time for training and validating, the time of performing the experiments, yes, the vanilla transformer is faster, but it's not significant. This difference is not significant. It's just it's almost the same. Okay, so you can continue with this kind of investigation, okay? Now, I saw the results aqui, the results here were about Choque integral, okay? We have tried other kinds of combinations, simulating the product of the matrix, okay? Using, for example, instead of the sum, using grouping functions instead of the product overlap functions. But we do not have comparative analysis up to now, okay? So future work, explore new data sets, and now making a real comparative analysis with the vanilla transformer. Using other kinds of fuzzy integrals, for example, generalization of the Choquet integrals and other that we are working for several years with Humberto, Radical, Javier, okay? And the theory from the theoretical part, of course, properties and so on, okay? This part, the properties and so on, it's easy. I have already done. Okay. Short presentation. I thank you for your.
Yeah.
I think so.
Okay.
For the.
Yeah. Okay. So thank you very much. Okay. Thank you. Okay. Okay. So now we have the presentation, which will be online. Just a moment. Okay. We need to wait for a second from the technical point of view. So just a moment.
I am able to see you and I can hear.
You can hear me?
Yes. Now, yes.
Okay. Okay, that's fine. So good afternoon. And now we have the presentation entitled A Fuzzy Algorithm for Image Rescaling and its Comparison with Classical Methods of Digital Image Processing. And the presentation, the talk will be presented by Anna Rita Sambucini from Italy. So please, Anna, you can start the presentation.
Thank you, and good evening to all. The rescaling of an image is a widely studied problem in digital image processing. Usually, a grayscale digital image can be viewed as a matrix where the element in the position ij represent the intensity of the pixel in the grayscale, namely the luminance. During the acquisition of an image, the process is characterized by a natural degree of approximation and of uncertainty. There are several methods to perform the rescaling task. Some of these are based on mathematical interpolation, like bicubic, some with quasi-interpolation. For example, I quoted here the second paper of this list, where the sampling Kantorovich is introduced for this task, while in the first paper, the authors studied this problem using interval-valued fuzzy set theory. In this talk, I will present a comparison among the bicubic, the sampling Kantorovich, and the fuzzy methods for a set of images. And the results of this comparison are at disposal in arXiv in the third article quoted here. The values of the luminance will be rescaled and normalized in order to attain values between 0 and 1. First of all, we take the initial imaging and we resize this image with a program like GIMP or something like that. After we elaborate the rescaled imaging with the bicubic, the fuzzy algorithm, and the sampling Kantorovich, and we obtain the reconstructed image, and we compare the initial image and the reconstructed one with some indexes. There are, in particular, with the peak signal to noise ratio indexes and the likelihood indexes as that can be introduced in a while. Another information I want to do is that the element outside the matrix for our image are set equal to 0. And both the fuzzy algorithm and the sampling Kantorovich algorithm are of special type, namely to determine the value of the destination pixel, not only the values of the original pixel in the initial image are taken in consideration, but also the value of some pixel close to them. Before to introduce the comparison, I would like to give some mathematical tools and key ideas of both the algorithms. For what concerns the fuzzy algorithms, the authors associated to each pixel an interval-valued membership using the lattice of subintervals of 0, 1 with an order relation and the Atanasov operator of parameter alpha, where alpha is between 0 and 1. So for each pixel, they construct using this function f an interval-valued membership in this way. X, the variable x, is the luminance in the assigned position. Y is the oscillation of the luminance in a neighborhood of the pixel assigned, and delta is a parameter assigned a priori and is an adjusting scalar factor for the oscillation of the luminance. The interval valved membership is constructed in this way, and using the Atanassov operator, it's possible to pass from an interval valved fuzzy set to a fuzzy set in such a way. So the key idea of the fuzzy algorithm is the following. For every pixel, if the magnification is of order 2p plus 1, we consider a grid, a square grid of this type. If the grid falls outside the original matrix, we put equal to 0 the missing pixel. Okay, so we construct this grid. The element of this grid are called V, K, L of Vj. For each grid, for each element of the grid inside the original matrix, we consider the oscillation of the intensities. We construct the interval valved membership, and using the Atanassov operator, we construct another grid with the same dimension of this one that permits to obtain the magnified image for the original image. So we substitute to the luminance this new grid, obtained in this way. For what concern instead the sampling Kantorovich algorithm, the first task to do is to associate to the matrix a function defined on the whole space R2 in such a way. This function is locally integrable and such that this operator SW of F is convergent. The function key is considered is a kernel with suitable assumption. Usually, or at least in this talk, we'll use as kernel the Jackson bivariate kernel given in this way. The Jackson kernel has two parameters, n and alpha. We assume for n the value is 12 and for alpha equal to 1, since in another paper we have observed that these are good values for the magnification. The value W better is for the value W. For the value of W, we know that if we increase the value of W, the representation and the magnification assumes better value. Okay. So for the sampling Kantorovich algorithm, we consider three values of W, 15, 20, 25, n and alpha are fixed before for the bivariate Jackson type kernel. At the beginning, we construct the function f. We apply the discrete convolution, so we obtain the sampling Kantorovich function f that can be rescaled and resampled in a number of nodes accordingly to the zoom factor considered. For what concerns the evaluation of the performance, we consider two similarity indexes. The first one is a fuzzy one proposed in the paper quoted below, and is a number between 0 and 1. For closer images, this index should be as close as possible to 1, while the second index is the peak signal to noise ratio. is expressed in terms of logarithmic scale of 1 divided by the mean square error. And for the evaluation of the three methods, we consider the following set of images which have different sides. As said before, for the PSNR index, we have fixed the values of the parameter n, alpha, and w. For the fuzzy type algorithm, we consider 100 values of delta uniformly distributed in the interval 0, 1. The corresponding values of the PSNR and the S index for the 4 images is given here. Obviously, the performance of the fuzzy algorithm depends on the values of the parameter delta. In the considered case, it seems that the curves in this study are concave, and they achieve their maximum in the middle zone of the interval 0, 1. In this experiment, if we consider the scaling factor equal to 5, the point of maximum are shifted toward left. To provide a more detailed comparison of the numerical result, we report here a table for the PSNR. In the first column, delta max represent the values of the parameter delta for which the maximum values for the PSNR is reached for the fuzzy algorithm. While in this second table, we have an analogous results for the likelihood index S. Based on the analysis of these two tables, it seems that the fuzzy type algorithm performs substantially better than the bicubic method, while in general the sampling Kantorovich method for sufficiently large values of W performs better than the two other methods, except maybe for the bot, since here for the bot, when we have the S index, we have the same values when W is 15. Here only for example, I have reported the image, the small image, and the reconstructed image for the case the magnification equal to 3. For the baboon and the city, we obtain the same values for delta max, while for the boat and the mountain, we obtain two different values for the sampling, for the fuzzy algorithm. We have also give some results for two images when the factor magnification is equal to 5. These are the results. And finally, we have also performed the CPU time of each algorithm for each image. What we have seen is that the bicubic is the more rapid algorithm. The CPU time for the fuzzy algorithm is good enough and is reasonable in sense of application, while for the sampling Kantorovich algorithm, this is weak results, since the CPU time is depending on the size of the image and also of the size of the value W. So it seems that in order to obtain the better representation, a better magnification, the CPU time is the price to pay in this case. And with this slide, I conclude my presentation, and I thank you for your attention.
Thank you. Thank you, Anna, for your presentation.
Thank you.
Any questions, remarks, observations? I don't see now. Okay, I don't have any question here also. So Anna, I would like to thank you for your presentation.
Thank you to you.
Thank you very much once again. And now we have the fourth talk about the aggregation functions and their association with linear splines. Will be presented by Andrea Stutanova. Andrea, you can start. Thank you very much.
I will speak about the relationship between aggregation function and linear spline. We can see from the title of our presentation. We start with some motivation. Linearization is very useful and common tools for creating mathematical models for many practical problems. For example, in the one-dimensional function on some small interval. Small interval can be approximated by its tangent line. For two-dimensional functions, we consider tangent planes and so on. In the case when a global approximation to be proposed, linear splines are standardly considered, and of course the continuity is the standard property or standard constraint in this case. We will deal with functions or with aggregation functions only on this NRE unit square. And that means piecewise linear functions, which we will deal. F is so defined when we consider finite simplex division first with k elements, and then the considered piecewise linear functions is linear on each simplex. That means can be expressed by this formula. For example, in the two-dimensional case, when we consider two simplices, we have only two possibilities. How can we divide it? The square, 1 and second. That means we have two. We have two possibilities when here is A, B, C, and D. Of course, in generally, this function is not aggregation function, only if A is just 0, sorry. If A is just 0 and the value D is just 1, then we get aggregation function. Special in the first time, we get the Schottky integral, for example, and in this second case, if B plus C is just 1, we get weighted arithmetical mean. Moreover, if we put B and C 0, we have T norms, minimum, in the second case, Lukasiewicz. On the other side, if B and C we put 1, then we get T conorms, maximum and Lukasiewicz. Note that in the special case where A, C, and D are 1 and B is 0, we get some fuzzy implications. And in this case, we have some Schoeffer-Stroh. If we still in the binary case, but we consider 4 simplices. Here is special linear splines with the node F1, where the value here is 0, 0, 0, 1. And in this point 2/3 and 3/4 is parameter alpha. This function is still not aggregation function in general, only weak aggregation function. If we want aggregation function, then this parameter alpha must be from interval 0 and 2/3. In this case, this function is semi-copula 2. If parameter alpha is from this subinterval, then we get quasi-interval and quasi-copula and copula 2, but never we get T-norm. That means aim of this contribution is study and characterization of linear splines, which are also aggregation functions. Firstly, we will focus in binary case for typical types of aggregation function, typical subclasses as a triangular norm, copulas, and so on. And second, we will deal with aggregation functions which are represented as some integral with no condition on dimension. First, we recall the properties of linear splines. Note that linear splines are closed under composition, therefore they form a lattice. And if some function f is linear spline, then its dual function so defined is linear spline too. That means if we have the characterization of T-norm, which are linear splines, then we have the characterization of T-conorm too, using the duality before T-norm and T-conorm. Okay, we start with piecewise linear triangular norms. This type of aggregation function, the characterization of this type of aggregation function is very easy. We have full characterization of this aggregation function. From continuity, we know that each such T-norm should be an ordinal sum of continuous Archimedean linear spline T-norms Ti. And what about this Ti? Their additive generators of this Ti should be piecewise linear and bounded. That means this Ti must be nilpotent with piecewise linear generator. The simplest case, of course, is the Lukasiewicz T-norm. Here we can see the piecewise so defined piecewise linear generator T and the corresponding T-norms, which we denote by T1. Other case of piecewise linear T-norm, we can see there, this is ordinal sum when here is Lukasiewicz T-norm. Note that this function, which we denote T star, and the previous, this T1, are also copulas. The situation when we deal with copulas, and we will study how looks like the copulas which are linear splines, is more complicated. What we know? We know, as in the T-norms, M ordinal sum of linear spline copulas is again linear spline copula. This holds not only for M ordinal sums, but for W ordinal sums too. But for pure ordinal sums, this is not hold. For example, here we can see W, where this W is the weakest copula, W ordinal sum when here is a minimum. In general, if copula C, if C is copula, which is also linear spline, necessarily this C is singular copula with support consisting of finally many segments. But this is not enough. This is not a sufficient condition, how we can see in this example. Here we can see copula C1, which is of course not linear splines, but the support of this copula consists of these three elements. The characterization of this class of aggregation functions is still open problem. We have only a hypothesis. The continuous function C is a linear spline copula if and only if support of C can be split into finally many segments, but with constant densities. We recall again the T norm, the function T star, this is T norm, and this T norm, the support consists with these three elements, but with constant densities. Here is A, here is 1 minus B, and here is B minus I. Okay, now we return our attention to the aggregation functions, which can be expressed as some integral based on fuzzy measure. The fuzzy measure in our presentation we denote by this mu. First, we recall three basic fuzzy integrals, which it's very known. Choquet integral, where by this way we denote such permutation. Sugeno integral, Shilkret integral. All these integrals are linear splines too. We visualize them for the binary case when the fuzzy measure is defined. This measure in 1 is A, measure in 2 is B, and A is less than B. Then we get Choquet, Sugeno, Shilkret integrals. Okay, Choquet and Sugeno integrals are special decomposition integrals. Decomposition integrals were introduced by Even and Lehrer. These integrals based on some decomposition systems. And then these integrals can be expressed by this way. For Choquet integral, this decomposition system contains only from a chain, maximal chain. For Shilkret, this is only singletons. And not very hard to show that for any fuzzy measure and any decomposition system, these integrals is a linear spline. Similar claim we get also for super decomposition integrals, which was introduced by Radko and Lee. Other very important, very now classes of integrals are universal integrals, which was introduced Clement Messier-Pas. And Sugeno and Shilkret integrals are also universal integrals. These integrals is based on some semi-copula, and then such universal integrals are defined by this way. Sugeno is based on the semi-copula minimum, and Shilkret on the product. But the class of universal integrals, which are linear splines too, is only subclasses of universal integrals. For any fuzzy measure and semi-copulas, such semi-copulas that for arbitrary element from unit interval, this function f, so defined, is continuous and piecewise linear. Then these universal integrals is a linear spline. Clearly, if this semi-copula is just linear spline, that means if linear spline, that means if, for example, is the function f1 from this previous example, or if this semi-copula is piece-bilinear triangular norm or piece-bilinear copula, then it satisfies the constraints of the last theorem. However, this property is not a necessary condition, which we can see in the next example. Here we can see a semi-copula, which of course is not a linear spline. But function f based on the semi-copula can be expressed by this way, which is continuous and piece-bilinear. That means universal integral based on this semi-copula is linear spline. Okay, only some conclusion remarks. In my talk, I will deal with only one approach to linearization, which leads to linear splines. We can use other approach to linearization inspired by positive homogeneity and which leads to so-called endpoint linear functions. This type of linearization was investigated in the paper with Radko, Messier, and Su and endpoint linear functions. This is all. Thank you very much for your attention.
Yeah. Thank you, Andrea. Any questions? Remarks? Because I'm working on implications, just I wanted to ask you wherever you have tried also to, we have considered the norms and the copulas, but have you tried to think also about the fuzzy implications or not? Aggregation. Okay, okay, thank you. Mm-hmm. Yeah, and you can just. Mm-hmm. Okay. Okay. Thank you, Radko. So thank you, Andrea, once again. Thank you. Now we switch to Spain, and we are on time. So we have the presentation of Juan Vicente Vieira from Mallorca. The title of this presentation is On Aggregation Function Based on Admissible Orders on the Sets of Discrete Fuzzy Numbers and Discrete Z Numbers. So Juan Vicente, you can present.
Thank you very much, Michael. This work is going with my colleagues, Sebastián Mazanet, Arnau Mir, Juan Vicente Riera, both of them the University of Balearic Island, and Laura de Miguel of the Public University of Navarra. So here you can see the main points of this talk. Firstly, we give some ideas about the motivation of our investigation. Then we explain some necessary preliminaries in order to understand them better in this talk. Then we present two construction methods based on discrete aggregation function defined on a determinant class of affinity chain. And finally, some conclusion and some possible future works. The construction of families of aggregation function on bundle lattice is according to Hop doctrine. So the introduction of the concept of admissible order have opened new research lines in the study of different families of aggregation functions on total order sets based on this family of linear orders. Here, the discrete fuzzy numbers are concretely those whose support is a closed interval of affinity chain Ln have been widely investigated, since they have proved to be useful for designing several computational linguistic models. The algebraic structure on which this linguistic model were based on bundle lattices where the partial order defined from the min and max function. So in this framework, several types of aggregation functions have been studied. Admissible order on the set of discrete fuzzy number, as well as on the set of discrete fuzzy number, have been investigated recently. Now that admissible order on this set are available, this computability model may be enriched. So the main goals of this talk, here you can see, we introduce a novel construction method of aggregation function based on admissible order in the set of fuzzy numbers with a finite set of membership values. This property is essential. And the second one, a new construction method of aggregation function based on admissible order for the set of discrete fuzzy numbers whose components have a finite set of membership function. Also, we show that this proposed aggregation function in this framework fulfill the same additional properties that are satisfied by the underlying aggregation function on this chain. Here you can see the formal definition of discrete fuzzy number, a discrete fuzzy set that satisfy these well-known properties. Here you can denote the set A1 Ln, the set of discrete fuzzy numbers whose subset is a subset interval of the finite chain Ln. In particular, we denote evaluation based on the Fn, discrete fuzzy numbers, any discrete fuzzy number belonging to this set. Here in this set, the expert can spread the opinion more flexibly. Here you can see a single linguist term high and a possible flexibilization of the linguist term high. In the case of theta numbers, Thade introduced this concept in under the model is a special class of sentence. Formally, a theta number is a pair of discrete fuzzy numbers, and in particular, where a theta number is associated with a real value and certain value, the first component, this one, playing the role of fuzzy restriction of the value of this real value and certain variable. And the second component is the imprecise estimation of the credibility of the first component. Here you can see an example. Likely, the time that we will take to go from Palma to Listowski Jam will be about 9.5 hours. In this case, here you can see the Einstein time available travel time, the first component, the quantification of the time, about 9.5 hours, and the second component, say the degree of certainty, credibility of the first component, likely in this case. In this case, the theta evaluation is denoted by this triple travel time, about 9.5 hours, likely. It is possible to use discrete fuzzy numbers instead of theta numbers. In this sense, the idea is similar, and we can modelize sentence have this one. Certainly, the investment profit on this business will be very high. Can be interpreted in this case as the theta evaluation, investment profit very high, surely. In this case, we have used these families of the linguistic says, and this couple are modeled by these discrete fuzzy numbers. Now we will present two construction methods based on discrete aggregation function defined on a finite chain. Our first result is the one. If we denote this set, A1 ln times EM, the subset of discrete fuzzy numbers, we suffer a closest subunit interval of the finite chain L, but whose membership values are in this set. In this case, it is possible to compute the total of discrete fuzzy numbers of this set. In this case, the computation, we obtain this number. So our first immediate result is if we consider an admissible order in this set, this set is a finite totally ordered set with the minimum element is this discrete phase number, and the maximum is this one. In this case, note that this symbol denotes the unit discrete phase number whose super is given by the single 0 and n, where 0 is the minimum element of the finite chain, and the n is the maximum element. In particular, this set is a finite sublattice of this lattice. So here you can see the classical definition of aggregation function in this framework. However, the idea is how can aggregation function be construed in this finite bounded lattice? The idea is this one. If we consider a concretely finite chain LK, where K denotes this number. This number is computed, but this cardinality means 1 in order because the beginning is the 0 element. So we define this function, the function position, and then our first result is the function position is an ordered isomorphism. That is, if we consider two discrete phase number where A is less than B, then conserve the position. So now we can construct a binary aggregation from a discrete aggregation function as follows. In this case, we consider an F, a discrete aggregation function in this finite chain, where K, the maximum element, is this number. In this case, if we apply this formula, we obtain the next result. This binary operation is an aggregation function in this bounded lattice. Here we can see an easy example. If we consider this finite chain and these possible values of the membership function, if we consider this discrete phase number A and B, well, it is possible to compute the total discrete phase number in this set, and then we compute the positions, and then if we consider the Lukasiewicz norm or the Lukasiewicz conorm, we obtain this discrete phase number on the other one. One interesting property is the preservation of the properties. So in this case, if we consider an aggregation function that satisfies some well properties, for instance, commutative, associative, idempotent, disjunctive aggregation, or conjunctive aggregation, then its extension, this new aggregation function, satisfies the same properties. In particular, if we consider a T-norm or a T-conorm or a discrete uninorm, the new aggregation function in our new lattice is also an T-norm, a T-conorm, or a uninorm. Now we will study the construction method in the case of theta numbers. The first one is the set of discrete phase numbers whose components are discrete phase numbers with finite support and a finite set of membership values. Here you can see in this case L4, this finite chain, the first component, and A5, these possible membership values, the other finite chain, and its possible membership values. Then this couple belonging to this set. Now that the linguistic interpretation is the main idea is the same. For instance, if we consider this sentence, surely that the investment profit on this business will be very high, can be interpreted in this case as the theta evaluation, investment profit very high, surely, where in this case, the set of linguistic terms are this one. Now, the idea of construct aggregation function in this subset of discrete theta numbers is to construct a total order. So the authors previously have investigated a form to construct total orders in the framework as follow. If we consider a theta evaluation and a total order in this set, we define this function, where we use, in order to define this function, a strictly decreasing function that satisfies this condition, and the function omega obtained as follows. So, using this function, it is possible to consider a total order in the set of theta numbers whose components belonging to this set as follows. This binary relation is a total order in this set. The authors previously have proved this result, then uses this total order. It is easy to prove that the maximum element of this set is this one, and the minimum element of this set is the other one. Similarly, in the case of discrete fuzzy numbers, it is possible to compute the number of theta evaluation in this set. The number of theta evaluation in this set is doable by this expression. And then, similarly, if we consider, in this case, a total order in this set, then this couple is a finite totally organized set with the minimum element is this theta evaluation, and the maximum element is this one theta evaluation. And in particular, this set is a finite sublattice of this lattice. Now we will construct aggregation function in this framework, and similar in the other case, we consider in this case a concrete finite chain LQ. But in this case, this is the cardinal. Means similarly, we have the function position, and the similar in the other case, this proposition is satisfied. So the function position is an ordinary isomorphism. Here you can see the formal definition in this framework. And it is possible to repeat the same argument, but in the case of theta numbers. If we repeat the same argument and you use this formula, it is possible to prove that this binary operation is an aggregation function in this set. Also, when the discrete aggregation function is a commutative aggregation function, or associative, or idempotent, or disjunctive, or conjunctive, also its F satisfy the same properties. As a conclusion, we have investigated several aggregate structures in the set of fuzzy numbers and third discrete theta numbers with finite supper based on admissible orders. Then, for each of these linguistic models, we have proposed an e-construction method of aggregation function based on admissible order, and we also investigate some classical properties of these operators. As a possible future work, use these approaches in decision-making problem. Thank you very much.
Thank you very much, Vicente. Any questions, remarks? You only showed that there are two results about the how many elements do you have? Yeah, that's the exponential growing. If you consider this one, or
no, on the pending, no. It is a problem from the computational point of view. But in the case of we consider only 10 15 membership values
Okay.
is not computermente complex.
Okay. Okay.
Then,
So only for the bigger numbers.
yeah.
Okay.
Yeah, but in the traditional spares, only one use
7.
little 7, 8, 9, 10
Okay.
finite values.
Okay.
For instance, 0.1, 0.2, 0.3,
Okay.
0.4. Then, in our opinion, it is possible to compute
Mhm.
easily all the discrete Fuzzy number or all the theta numbers to ordain
Okay.
this one, and then use this ordination in order to construct
Mhm.
the aggregation
Aggregation.
function.
Okay.
This is the main idea.
I see.
But of course, if the membership function is many
Element. Yeah.
elements,
Yeah.
maybe it's a complex computational problem, and
Yeah. Okay. Thank
but
you.
in real problems, it's not necessary from our
Your
point of view.
Okay. Okay. Thank you very much. Other questions? If not, once again, thank you, Juan Vicente. We remember the speech from the EUSLAT, yes? Okay. That speech is from the for mentor? For mentor. I remember. Okay. 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 So now we can switch to the last talk, last but not least. There will be a speaker from Poland, from Rzeszów, Paweł Drygaś, with Anna Kroll, in cooperation with Anna Kroll, some kinds of thresholds generated fuzzy implications. So Paweł, the floor is yours, please.
Thank you. As you say, that's common work with Anna. And in fact, we present here the construction of fuzzy implication from given ones. That we have a family of fuzzy implication, and we want to obtain the new implications. And next, we ask about some kinds of properties which are preserved by this construction. So first, I put the definition of fuzzy implication and fuzzy negation. Next, I remind some construction of ordinal sum of fuzzy implication, because this construction will be closely related to the ordinal sum of fuzzy implication. And next, I want to present the two construction methods and preservation of some properties of implication by these two construction. And at the end, some conclusion and some future works. Fuzzy implication is a binary function which is monotonic, that is decreasing with respect to the second variable, first variable, and increasing with respect to the second variable, and repeat the boundary condition. And directly from this, we obtain that in the left and the top border, we have 1. And so next, I remind some basic properties which will be used later. That's consequence boundary, that's in the right side, values are greater than y, and neutral property is equal y. Identity principle, that's in main diagonal, the values is equal to 1. Left ordering property, that for above the diagonal we have the values 1, and right ordering property, that if values is equal 1, then we are above the diagonal. Directly from these two properties, we have ordering property and boundary condition. Strong boundary condition, that means that in the bottom we have the value 0. The strong corner condition for 0, that means that 0 is only on the right bottom points. The strong corner condition for 1, it means that 1 is only on the left or on the top side. Only in this place when we need to have 1 from the definition. So the basic example of implication which will be used in the next examples are Łukasiewicz, Gödel, Rashidini, Weber, Gauguin, Potter, and this implication will be used in the construction. And okay, negation. There is the decreasing function which fulfill the boundary condition. In 0 we have 1 and 1 0, and the greatest and the least passive negation. So we have the standard negation, which is evolution. There is a example which will be used later. Of course, for every fuzzy implication, we can define the negation, which is called the natural negation of fuzzy implication. This is the values of the bottom part of the unit square for the implication. This is the values. And now we go to the different kind of construction connected with ordinal sum. In fact, this construction proposed by Bastian Jante is connected with implication which, for Jaeger, which is connected with generators. That's like for T-norm. For norm, we have a generator. Next, we join this and we obtain the generator for uninorm. Similar, here we have such kind of implication, but instead of such implication, which are generated, we can put here arbitrary implication. So we join arbitrary, divide this query to two parts and obtain the fuzzy implication. The picture is easy. Here we have 1, and next we have a 1 and a 2 implication. The next construction is similar like for triangular norm. So we have a family of subinterval of interval 0, 1, and in the all square connected with this interval, we put scaled implication from family of implication. And on the rest, we put the Gödel implication. In the T-norm, we have minimum. Here we have a Gödel implication. But unfortunately, for construction of ordinal sum of T-norm, we can put arbitrary T-norm. Here, we must assume that summands fulfill conditional boundary condition. So not all implication we can use as a summand. Of course, if we change this from Rescher implication, this implication, we not need such assumption. So we have such construction, and there is here you have summons and Gödel implication. Another construction is connected with the ordinal sum of overlap function. So we put one in this left side when we need one, and in this square we have scaled fuzzy implication, and such values maybe better will be seen in this picture. In the left side we have the upper bound of this interval, and in the right side we have values which we have on this boundary. So for arbitrary points y, we have the same values as in this point. In this line is the same values, and on the rest we have y. This is similar like for overlap function, and this operation is of course fuzzy implication. A completely different approach to the ordinal sum construction is given by Zhou, and here we have a such situation that we put some region on unit square and put here arbitrary function, not necessarily arbitrary, but the function which preserve the order, which is decreasing with respect to first variable, increasing with respect to the second, and such that this function also preserve order preserving. But this is a special kind of order. I not put all this detail of this because in the application there is 2 pages of this assumption about this construction. There is difficult to put in one slide all this. And as example, we have, for example, we have the ball and Klein, Dini, and Fodor implication. Then we can construct such application. Here we have this, and the only difference between the application is that here we have the y and 1 minus x in these parts. On this triangle, we have the same values in original application. But in my opinion, this this construction is too general that we can say that we can put everything that preserves the monotonicity. That is such kind of such idea of this construction. So let's go to the results. First, there is a very small modification of the construction given by Sebastian. There is only in this part, instead of put value in if y is e, this implication we put its implication. There is, okay, I have now the picture for this, but in fact, we use this construction to the next construction, because here we put not close or open or left close left open interval, but this means that here we can put arbitrary closed, open, left open, right open interval. The only assumption is that these interval are disjoint. And we construct scale only the second variable. Similar in the previous construction. And on the rest, we put the values y. And in fact, here we can put different kinds of implication. And in this line, we can choose which values will be for this or for this implication. In fact, we can relate these parts because we can put the implication ID which has such kinds of values. And what we could say about this construction first, in fact, the values of these parts belong to this interval, of this interval. This is one of properties of this construction. And another, if we have such construction, then we have that this construction preserve consequence boundary condition and neutral property condition. These two conditions are preserved, but if we look for another properties, there is more problematic. Identity principle is satisfied by this construction only if we have one summand. Now, it's not very interesting situation that this application, this summand must fulfill this identity principle. In fact, the difference between the original implication and obtained by this construction might be only on the bottom part of these implications. For left ordering property, we have similar situation. For the right ordering property, in fact, this depends on the case when the end of one of these interval is equal 1 or not. So in this case, if there is not, always the construction fulfill the obtained implication by this construction fulfill the right order property. But in this case, we need some scale of this property on the top application. And directly from these two previous properties, we obtain that ordering properties satisfy only in this case. And the next three properties are connected with boundary condition. And again, if zero not belong to this family of interval, of course, AK may be equal 0, but 0 may not belong to this interval, then I satisfy this strong boundary condition. And if 0 is in one of these interval, then this implication must fulfill the strong boundary condition. The strong corner condition for 0 is fulfilled only if 0 belong to the one of interval, and this implication fulfill the strong corner condition for 0. And if we consider strong corner condition for 1, we have again two cases. If all interval are ends of interval are different than 1, and if 1 is equal to 1. Here we have this condition is fulfilled, and in the second case the summons implication must fulfill this condition to obtain implication which fulfill this strong corner condition for 1. Okay, here we have some kinds of continuity which is connected with construction of implication with using the continuous implication, because if we scale the implication, then in the left side, on this kind of point, we obtain the discontinuity point, and similar also in the next theorem we consider the continuity, and for this theorem we have the natural negation of a implication obtained by this construction. In the case when 0 not belong to any of the intervals, we obtain that natural negation of implication is n0 implication. And in another case, if 0 belongs to the sum implication, we obtain natural negation of implication as built using 1 in this point, which is needed from definition, because in the left part we have 1, and here is scaled natural negation of the summand. Okay. But in fact, for this construction, outside of the sum of interval using for sum on this question, we use ID implication. We use, in fact, the value is y, and the question is if we want to obtain use such construction E and use this implication, which implication we can use here? Yes, and answer is this implication must be. This is only possibility. This implication, and in this case, we obtain y in these parts when we not have a summand. But if we look for the paper of Saul, then we can consider another situation. Here, this implication is good for arbitrary set of interval, arbitrary family of interval. But if we take the fix the family of interval and family of implication, then of course we can put here another value. In fact, these values should belong to this interval. Only things with which we need is preservation of the monotonicity. Of course, these values in this interval belong to this interval. But in fact, instead of this, we can take arbitrary rejection, which put another values. So the values will be not in the diagonal, but can be below or above this, or in different ways. So in some parts we can take the greater values and another in less. Okay. In this presentation, I put some method of construction of implication and put some basic properties. And in the future work, we want to characterize the implication generated by this construction. Which kinds of implication we can obtain by this? What is the connection between the known classes of fuzzy implication? Also, we want to look for some application of this family of fuzzy implication. Thank you very much for your attention.
Thank you, Paweł. Thank you very much. Any questions? Remarks? I only want to maybe just to underline on just to say that because we have also some joint paper with I have also joint paper with Paweł about this ordinal sums. If we have the T norms, then of course the ordinal sums are important because they are useful for the representation of the continuous T norms, and this is the reason why ordinal sums are mainly such important. Yes. And of course, we have also several generalizations, but in the case of the implications, we are still looking for the firstly characterization of such class of functions. And secondary, of course, we can construct maybe also some other classes. But the main question is what you have written on the previous, on the conclusion about the characterizations and what kind of the problems we can, in which kind of problems we can use the ordinal sums. I think that this is still the open problem where the ordinal sums or what kind of the construction of the ordinal sums can be useful from this point of view. This is not the question, of course, but I know that this is a hard problem, but I think that this is quite important one. That's the only one.
Yes, I agree with this. That's
yeah.
There is some construction, but there is no such theorem like for T norms or for norms.
And of course, we cannot have such a theorem for the continuity because the ordinal sums for the implications are not continuous. But the problem is what other maybe classes can be characterized by such construction methods. But still open problem. Okay. Some other questions? If not, thank you, Paweł, once again. And please remember about the registration for the bus. And as soon as possible, not later than tomorrow morning at 9. You can still switch between different trips. And I wish you a nice evening and also bon appetit. Thank you. Thank you very much.